Let's talk about how object hierarchies are held together. Office documents have lists of pages and page contents. GUI consists of forms and controls. Databases have tables and indexes. Compilers operate on abstract syntax trees. All these data structures have something in common: they are organized in a tree-shaped hierarchy, where each object has exactly one owner. This type of relation is a well-known composition. In UML it's portrayed as a filled diamond arrow.
Argentum has a special composition pointer, the owning pointer. Every time you declare a class field initialized with an object, it's an owning pointer field. These two declarations look similar, but they are slightly different. This one is a local temporary pointer, while this one is an owning pointer field. Two temporary pointers can reference the same object, but owning pointers cannot. If allowed, it would violate composition single-parent invariance. So it's checked at compile time. This expression yields a temporary stack pointer, which is incompatible to owning pointer by assignment. In order to assign something to the owning pointer, it should be of type owning pointer itself, meaning it must be a new object, not owned anywhere else. This includes a new instance, a copy of an existing object, or an owning pointer result of a function or block. Argentum's copy operation mentioned in the previous chapter handles object hierarchies as well. It makes a deep copy of the composition subtree, because shallow copy violates composition invariance. And Argentum's goal is not only memory safety, but also the higher level object hierarchy safety. What happens to the previous value stored in this field when we assign here a new value? It is disposed immediately, since it's not retained in any temporary pointers. In contrast, this previous value is retained by local variable x. So it's deleted here. In most real-life cases, an object can have a variable number of child nodes, a document can have an indexed list of pages and a key-value set of styles. It's represented with an array and map of owning pointers. All operations on collections items are totally identical to the operations on scalar owning pointers. What about memory leaks? Owning pointers manage tree structures, handling creation, disposal, assignment, and deep copy operations in a way that prevents pointer loops. An object subtree lives as long as its root is accessible via a temporary pointer. Since, as proven in the previous chapter, temporary pointers are destroyed when they go out of scope, owning pointers ensure no memory or resource leaks. You may say that application data structures are not reducible to trees. You are right, there are types of object relations other than composition. We'll discuss other pointer types in the next chapter.